Okay, the final part of chapter 19 is about transformers. Beautiful little bring together of all the ideas from earlier on in the chapter. So what we're going to look at is very briefly just go through the notes, mainly very GCSE-ish, the idea that the voltage on the first coil, however many loops it's got, creates a voltage in the second coil dependent on how many loops it's got. Okay, so we'll go into a little bit of detail, but most of it is actually straightforward stuff from GCSE. The bit that matters. The key point for us, which makes this slightly more detailed, we don't need to go into a lot of detail, but slightly more detailed, is the idea that you've got something that causes this magnetic link. Okay, so it's all about the idea of the flux flowing back and forth through here. Why? Because in a way we've got to work backwards from here. If you want to get yourself an EMF, okay, if we want to induce an EMF, then we need to have changing flux linkage. And so if we have more coils, we're going to have more flux linkage. If we get a better flow of magnetism, we get more flux linkage. And if we have more magnetism, we're going to get more flux linkage. Okay, so the idea is all about how we optimize the amount of energy we can trap with our second coil. Okay, again, I'm not worried about coil solenoid here, it's just loops. Okay, so the crucial bit, nice and straightforward. We need to basically have this idea on how a transformer works. So what I'm going to do is jump down a little bit. You've got some details here. Okay, so I've got some descriptions, you can read it out, work it backwards, etc, etc. The key bit is certain characteristics make it work better. But as a step up, I would get into your head a key 3-step process. Okay, and the first bit at the beginning actually depends on the end. And this is how transformers work for everything. So voltage will be induced when you plug this in, like with a phone charger or an old phone charger or your laptop charging lead. That will always be flowing as soon as you plug it in. You're always going to be creating a voltage as soon as you plug it in. However, it's not till you plug a device in at the end that you then draw the current. And however much current this device needs at the end controls how much current comes in at the beginning. Why? Because in the end it's all about energy. So you're going to put energy in, you're going to put energy out. More importantly, we'll call it power, because how much energy each second makes more sense. So power in, power out. That transfer of, or the rate of transfer of energy all the way through links in with the rate of change of flux. So I'm going to work backwards. So this is how the transformer works, input through to output. Okay, so let's just put that in. I know some of you, I did the notes the other way round, but I'm going to just work backwards. Okay, so I'm going to actually start with here, so I'll number it. So we need to create a voltage at the end. We need to induce an EMF, and so what we need is a changing, I'll say changing rather than alternating, a changing flux, can get that phrase in, flux linkage. Okay, so crucial word, usually a hyphen in the middle. So with a changing flux linkage, whether it's alternating current or, okay, I'll put in brackets, or switching. So we could just have DC but switching on and off, as long as you've got some change going on. However, most of the time, 99.9% of the time, we're looking at alternating current because it comes from the generator. So that changing flux linkage, and because we've got two coils, let's make it clear, in the second coil, okay, usually the secondary coil, but second coil will do, will of course induce, or to make this make sense, induces an EMF. Okay, so that voltage will be there, the current isn't necessarily there. Okay, so going backwards, how do we get that changing flux? Well, the step before means that we require a changing field flowing around. Okay, so you need to create a changing magnetic field flowing, and this is a crucial kind of bit, through to the second coil, flowing through, I'm going to say magnetic circuit, underline that, circuit to the second coil. Okay, so this is effectively a circuit. There is no electricity going through here, it's the magnetic field that's trapped. To make it work best, to make it flow better, you need something that has a high permeability. Soft iron, but doesn't stay magnetized, because that would use energy or require energy to change your field. So very, very soft, as they say, easy to magnetize and demagnetize, and it's this high permeability that matters, gives you a stronger magnetic field. Okay, so to get that step before, okay, so this is the key idea, it all works backwards from the beginning. You need a changing, of course, to get changing, okay, so that's that key link across the way. You're getting changing what? Well, you actually need current to create magnetism. Okay, to create that magnetic field, you need electrical current. So you need changing electric current in the first coil. Oops. So it's not the voltage here that matters, even though that's where the equation comes into it, it's the current itself. So you can't really have either of them without connecting it, so you're going to have one, you're going to have the other. So it doesn't matter too much. But yeah, it's that kind of crucial idea about the EMF, as I said there, and the current flowing that creates the whole lot. Okay? Sorry, higher up. Yeah, here. So those are your key steps. So we can link in equations with them. Okay, you can bring them together. We can think about the Buni here. We've got that idea of magnetic flux density, so we can start thinking about how do we get more flux. Well, again, we got the flux comes from BA. Okay, so we've got our link there. Here we've got our EMF is delta flux times by the number of coils. I'll keep it afterwards. It does matter, of course, the order and how quickly that changes. How do we get that flux? Well, sorry, how do we get the field strength? Well, we've got things like, I'll put it in the version that we have, so mu equals mu n I. So again, it links in with the number of coils. Okay, so voltage creates current. It also, worth pointing out, creates heat in the wires. We'll come back to that. And obviously current flowing here in these wires will produce heat. So you're going to get a little bit of energy loss, power loss from the resistance in the two coils. But the rest of it, if you design it well, is almost perfect, almost 100% efficient. It's little things that make a difference. So what we're just going to link in, have I said anything else? Okay, so I'm just going to put in brackets here that we've got our link, that's our magnetic circuit. And again, that's a quite powerful idea. Don't use the phrasing, but it's quite a powerful way of thinking about it. Electromagnetism, electromagnetism, electro is kind of stepping in back and forth, just like an electromagnetic wave does. Okay, and again, worth pointing this, because this is where Lenz's law comes in. So if you've got a current flow in the second circuit, if it's complete. Okay, so you're always going to get that voltage, but not necessarily current. So what that does is, if we bring the mathematics together, excuse me, if we bring the mathematics together, it gives us what you learned at GCSE. Step up, step down transformers are the same, just depending which coil you connect to the input voltage, the one with the more turns or the one with the less. So mathematically it's just ratios, and again, assuming we got a fairly efficient system, the voltage will always be correct. There are some limitations we'll come back up to in a second. So the crucial bit is you've got this link between the two. You've also got current as part of the calculation. That's not part of GCSE. Okay, so we need to bring them in. How do we bring them in? Well, power in equals power out. Electrical power, IV. So, okay, I'm going to put it there, IV. Obviously, power in is on the first coil and they're on the second. Okay, so input current and voltage gives us output current and voltage. Okay, how do we link them all together? Well, mathematics of it is that the ends come in with the voltage, so there's your voltage number link, and we'll get a very similar thing at the other end. So I'm just going to put at the edge here, it is in the PowerPoint, but put at the edge that basically E over N equals, and we'll go for the rate of change, so rather than delta, d phi by dt. So it's a bit more correct if you wanted them further detail, and that is true whether you are using a voltage to create the magnetic field or you're changing magnetic field to create your voltage. I should say that's true from the voltage if the voltage is changing. So as soon as you've got changing, you've got that link, which means that voltage 1 number 1 equals voltage 2 number 2. Simplifies to the version that you had at GCSE, which was simply that. I'll do it from the numbers point of view first, I think. So number in, again, it doesn't matter which way up. I'm going to say number 2, sorry, I've used P and S, so secondary number as a ratio compared to the primary number will give you that secondary voltage. I've changed to V now just to make it a bit easier, but again, it's induced EMF coming from your first voltage, which is actually a PD. So let's just say voltage. But we also need the fact that power equals IV. So what we end up with is, if voltage is going up for the same power, then current must go down. Okay, so we're getting the opposite effect, and you'll get it in exactly the same ratio, except it'll be primary over secondary. Okay, so that's going to be happening all the time, but if you are delivering energy to a device, then you're going to get this effect. So notice the other way up. So if this is increased, if the voltage increases about, say, 20 times stepped up, so 20 more turns, 20 turns on the secondary compared to every turn on the primary, you'll get 20 times the voltage, but to 20th of the current, okay, 0.05 of the input current. So it steps down, assuming it's efficient. Now in reality, not all the power gets transferred. You have your efficiency coming into it as well, and it affects the current output. Well, actually, working backwards, it affects how much extra current you need at the beginning. Okay, so depending on your current output, say you need 3 amps to make your bulb work, if you stepped down by 10, so you got 3 amps, you step down by 10 for current going backwards, okay, so 0.3 amps at the beginning, you'll actually need a bit more than 0.3 amps to get the right current at the output. Okay, the current of the output is just simply V equals IR. So whatever your resistance is, it will draw a current that requires the energy to come from the magnetism, that requires the energy to come from your input. So how much you have at the beginning, how much power at the beginning, depends totally on what you need at the end. Okay, you're not pushing the energy out, you're drawing the energy from whatever needs it, or whatever to whatever needs it. So that's the crucial bit, worth putting in, because I haven't labelled it anywhere, I don't think, where is efficiency as a fraction, okay, e.g. 0. And they're actually usually pretty good, so 9.95, they're 95%, 96%, 98%, you know, a lot of them are actually commercial versions are around about 98% typically. Okay, so really efficient machines. Okay, most of it, as I say, is lost from there. So if we have a think about that, I'm just going to go back to this a second. What does that mean? Well, if you want something like a machine on a building site, you will need usually something that's using electricity to create motion. You need typically an electric motor. I should say e.g. electric motor. How do you get a big force from your motor? You need a lot of flux. Working that backwards. To get a lot of flux, you need a big current. Okay, so that means large current. Okay, what that means is you need a smaller voltage. So you actually need to have a low step down transformer to give us a low voltage, to give us that large current. Okay, so that's to make it work. That's your need. So how can we make it work better? Well, step down transformer to give me a small, I'll just put it, so I'll do that in the other way. So small voltage. Okay, so we're going to need a small number of coils, but because we've got a large current, we want to try and reduce the resistance, because large currents, just put up there, remember, I squared R, power loss. Okay, so if we've got a large current, we need a really small resistance, big fat coil. Okay, going the wrong way around. So big fat coil where you need a large current. What that means is at the beginning, you're going to need more coils than you have there. Okay, so that will be stepping down. So more coils will give us more voltage. Okay, few coils here give us a lower voltage. The flux we just need to just be as big as possible, so we try and make this as many coils as possible. I should say the equation becomes more and more true if we have more and more coils. So again, if that's roughly, by the look of it, about a step down by a factor of 2, it's twice as many coils roughly. Then if we go up to instead of 4, if we have 40, and that would be 10 times more, it would work better. Okay, that will make it a more efficient magnetic field. But back here we've got more coils, so actually you're going to have more voltage. Okay, so this is going to be big, which means that this is small. And the key to find it out is that, as I said, you will need to multiply your input fraction by V1I1 to give you V2I2. Okay, so whatever happens here leads us to that, and that is how you calculate from your efficiency how much current. Calculating voltage is easy. It's the current that comes last. Okay, so this is your final calculation. Now that's not in the notes, but have a think about that. That depends on everything else. So, back in the notes, we've got some simple, we've got some simple bit of information. If we go back to what you did at GCSE, well, we usually have the step down transformer. I didn't actually put that, so that's a step down because the voltage is getting smaller. So you're stepping down the voltages. This is usually your final stage from the national grid as well, because again you want a small current, so you'll have a small energy loss. Back to our equation there, as it flows through the wires. So step up, step down. The key point is, it seems a bit of a faff, but it is to give a small current flowing through the wires because of that resistance. Okay, so cables of the national grid tend to be aluminium because they're a good conductor, but they're very light as well, so low density, so they don't sag from under the weight. Unfortunately, aluminium does sag, so they have a steel core, so it's the aluminium around it carrying most of the energy. But yeah, very light, very low resistance, very large cross-sectional area. Okay, so big fat wires. Okay, transformer itself, well, again, a lot of it's common sense. So efficiency is a thing that's just kind of keep in the background. Low resistance turns, as we mentioned. Wires, let's call it that. So why less, think of that phrase, nice if you can put it in, less ohmic heating. In other words, heat loss or heat emitted due to the resistance in ohms. Okay, so as I said there, that have got space for it, larger area for larger currents, or the larger current. Okay, we've mentioned the core being soft iron, so high permeability, as I say, it's not really in our notes, but it's that idea of low resistance for magnetism. So high permeability, which was that symbol we mentioned in the first lesson of the core. And that, what's the reason for that? Sorry, let's put the reason in. So that means more, I'll put it as symbol, more flux linking with reaches, excuse me, reaches secondary coil. Okay, and you also want it to be soft material. So iron is a bit noddy. We've moved on quite a long way from then. So if you really want to know, it's a nickel ferric material. So it's not just nickel itself, which is magnetizable, but it's a version, and I was about to say an alloy then, a compound that works better. So NFE3 for the chemist in the room. There we go. And the last bit is a laminated core, and I should say with insulation, so they're a very thin layer of varnish for most, with insulation. Oops, missed out a letter. Insulation between layers, because again it's the idea of you want the magnetism to flow. You don't want it to flow sideways, you want it to flow around the magnetic circuit. Okay, so this, run out of space there, but reduces eddy currents, not electrical currents, of magnetic field. So as the field flows itself. Okay. Eddy currents is where it's swirling back on itself. So again, if you had your core, let's say like that, and there we go, that kind of idea, magnetism as it flows round is just like any other fluid. If you get this kind of effect, twirling sideways or round sharp corners, so again real transformers tend to be quite smooth and rounded, that is an eddy current. And that is where energy is kind of being dissipated. It fights against each other. The flow fights against each other. So yeah, you lose energy. So again, the key point, as above, more N phi, more flux linkage at second coil. Okay, and that's all there is to it. That's really the key idea. And I say the most beautiful bit is these two, I think, because we know what's going on, why it's going on. We know how to get the magnetism and the density of the magnetism. I should say there as well, it's worth pointing out, I've not really put this on before, but laminated core of large cross-sectional area. So again, a big fat core, okay, will mean that you're going to have a lot more flux flowing through because of B times by A. Let's just put it in. Okay, so your magnetic field that you're making, your flux density, the more area of your coil, the bigger it's going to be. So big here, doesn't really matter so much around the top, but generally, again, smoother flow if you're not compressing it, makes it work better. Okay, and that is transformers. Lovely little end to the topic, which brings it all, as I say, together through those steps. Cheers.